Alright guys, in the last video we were talking about centrifuges and we said, hey, this is like washing machines or this is like salad spinners at your kitchen. So what goes on is that you put material on the inside and it spins. And the speed of which it spins is called RPM, or rotations per minute. And then we can keep them in there for very long periods of time or very short periods of time. But we said, warning, 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 if you spin too fast or if you spin too long, you actually generate heat. And heat could be a bad thing with your product, and maybe you don't want that to happen. So we were talking about the basics of centrifugation. That's what this was all about. And it led us into this discussion of a G-force, and it led into the discussion of how these centrifuges are somewhat doing their job the proper way. In this video, we're continuing that discussion, and the reason is because I think that it's very important for me to give you the difference between a lab centrifuge versus maybe more of a manufacturing type of centrifuge. Because as you can imagine, the laboratory arena is going to be very small. It's going to be all nice and little and dainty, and then we can put little bitty samples in it and we can spin them and we can do whatever, and we don't really have to worry about heat that much. Whatever the case might be, there's going to be smaller footprint. On the manufacturing side of the house, though, you are going to be looking at huge centrifuges. I mean, these things could be bigger than me maybe sometimes. And they operate, or they look a little different, but at the same time, they are meant to do the same purpose, and that purpose is to separate things for you. Most of the time, solids pulled out from the liquids and vice versa, but the idea of them is going to be the same. So some of the extra terms that will come in on the manufacturing side of the house are going to be basket centrifuges. And I want you to think of basket centrifuges as those types of salad spinners that we talked about in the last video. We don't really see those on the laboratory side of the house with lab analysts that stay in a nice little air-conditioned room and they're just like waiting on samples. Well, okay, those centrifuges are a little different. We don't necessarily see baskets a lot of times, but basket centrifuges can be pretty common on the manufacturing line. And these are just big salad spinners that we can just dump our bulk product in, and those are going to spin, and of course it's going to pull the liquid out from that solid. So that solid could be left behind, that solid could be captured, that solid could be processed, or again, the liquid that gets pulled off, that liquid can be captured, that liquid can be processed, and so forth. Other than basket centrifuges, we often talk about settling velocity as well. And settling velocity is just that. You know, okay, if I've got a little tiny test tube, and in that test tube I've got a liquid with some solid that has appeared that I need to centrifuge out. Well, if I just kind of leave it alone, or if I just let it kind of do its thing, work with gravity, this stuff is what we were going to call settle to the bottom, right? That's what this is all about. So that solid is going to settle to the bottom of that container, and that takes a little bit of time. That takes a little bit of patience. And because of that, well, we're kind of, wait. We're like waiting for grass to grow, for it to settle, blah, 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 and then I'll go and do something else. Well, that speed, or that slowness, but really the speed, aka velocity, is this thing called a settling velocity. So how long does it take in order for that solid to settle to the bottom of that container? Now, we can also talk about settling velocity as far as centrifugation goes, because now what I'm doing is that I'm not necessarily using gravity to do the work, but I'm actually using the centrifuge, which is going to amplify that velocity. It's going to make things speed up because we're pulling more force down onto that solid to settle to the bottom. Next up, as far as manufacturing goes, we do have a discussion with specific gravity and density. And these two things are not the same. Warning, 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 warning. They are not the same, folks. Specific gravity and density are quite different. So with that said, what is the difference, Tracy? Okay, well, I'll tell you. Density is just, I want you to think, it's not really the true definition, but I want you to think of maybe how heavy something might be. even though that's really a misnomer, I think that a lot of people go down that rabbit hole. And for us, that might be okay. I mean, that might be all that we need to think about density goes. So if I get a block of wood and a block of metal, and I'm going to hold one in one hand and one in the other, I'm going to definitely feel the difference. And that difference is going to be a little bit of weight for me, right? So this density is really going to be defined as D equals M over V. And that M is going to stand for mass, and that V is going to stand for volume. So I take the mass of the object and I divide it by how much space it takes up. And that's the definition of volume. So the density of water is close to 1. It is not exactly 1, but it's close to 1, right? And if anything is lower than 1, it typically floats. You've watched the It movie, or maybe David Letterman back in the day when I was growing up. Will it float? I mean, that's kind of the whole thing that he would do. And then if it's greater than 1, that means it's heavier than water, which means that it's going to sink most of the time into the bottom of that container. That is what we would kind of regard as density. And density is a great number. Density is absolutely something that we can use and that we can talk about and we can calculate. So I'm not going to stub my nose with density, but there's also another value, and that value is called specific gravity. And the difference with specific gravity, and I'm going to abbreviate this as SG, all right? So specific gravity is actually going to take the density of your stuff, whatever stuff that might be, and we are going to divide by the density of water. And the reason that we're doing this is we're creating a ratio, but I'm ensuring that all of this is actually at the same temperature. That's very important. So if these two things are at the same temperature, and I take the density of my stuff and I take the density of water and I divide these two things together, that is going to be called specific gravity. In a regular type of science course, what normally goes on is that they're like, oh, a density of water is 1.00000. So when you calculate density of a solid object, you calculate specific gravity because it's the same number. Warning, warning, warning. No, that's not the case, because the density of water is not 1.0000. So the specific gravity is actually not equal to the density value. They will be super close, but they will not be exact numbers. They will not exactly match. So it really depends on what we are referring to when we go down this discussion of will it settle or will it float? Are we talking about densities? Are we talking about specific gravities? If we are talking about specific gravities, that is not the same as density. These numbers will not be the same, and I can prove it to you in our laboratory spaces because we have an instrument that will measure density, and it also reports specific gravity. And it will do that calculation on its own, and those two numbers are never identical. So please keep that in mind. It is all about will it sink, will it float, and that is mass divided by how much space it takes up. And to us, it might feel a little bit heavier. And to us, if we feel something a little heavy, we know, oh yeah, that's going to sink. I know that. I don't need a calculation. I don't need D equals M over V and then divide by the density of water to calculate specific gravity. I don't need to do all that stuff. I can just use some common sense in order to determine that. Next up, another difference a lot of times in manufacturing with centrifuges is something called a continuous flow centrifuge. As you can imagine, we need big centrifuges in order to take bulk product. But at the same time, we want something that's convenient. We want something that can slowly take things, maybe little bits at a time to spin them down. And that really maybe will speed up the entire process in the long run. So these are continuous flow centrifuges. So those centrifuges are typically, I want you to think of them like big barrels barrels. I mean, you're just huge because we're doing bulk product, because we're on manufacturing. And we've got this big bulk product and we are dumping it down into a spinning salad spinner. That's what it is. And it just continuously goes. I mean, it really never stops. It just continually spins and spins and spins. Even when something's not in it, it could be spinning. And then it is spinning and it is ready for you when you're ready to make your dump. I mean, that's what this is all about. So as the product is coming in, it is just constantly kind of dumping into that continuous flow centrifuge, and it's constantly spinning and it's constantly pulling out liquid. And then over time, sure, it's got to be stopped, it's got to be cleaned, it's got to be emptied, or whatever the case might be, but it is continuous flow. This is very different than the laboratory setting, because with the laboratory setting, you actually don't see continuous flow that much. These are going to be countertop instruments. They have lids that open up. You put small quantities of things on the inside. You close the lid back, you turn it on, you allow it to spin, and then after that time is up, maybe it's just 5 minutes, but after that time is up, you go back, you make sure that it has stopped spinning, you open the lid and take out the contents. That is not continuous flow, right? You are stopping and you are starting multiple times, maybe throughout a lab exercise or a lab test that we've got to be doing on that side of the house. So slightly different. But again, the overall concept, I think, is pretty much the same. Another way that we can separate other than centrifuges is something called a liquid extraction. And sometimes these things are going to be called liquid extractions. And that's perfectly fine. But most of the time, people don't want to say liquid because it makes them sound a little crazy. So they just kind of say liquid extraction. And we know what you're referring to when you do that. So liquid extraction, as you see on the screen, is a process of adding a different solvent to a solution to pull a particular solute out of the solution. All right, well, solute is the stuff that is dissolved in the liquid, right? I mean, use your words, use your terms. I mean, that's kind of what we've done many videos back. And a solute is something that can be pulled out. And if I don't want to use a centrifuge, or if I don't want to use filters, then liquid extraction could be another option or opportunity for me. Again, pretty common, and it's going to depend on the manufacturing type of setting. Liquid extraction is also found on the laboratory side of the house. So lab versus manufacturing, again, that's what this is all about in a way. But the concept of them are very similar. As you can imagine, the laboratory side of the house would use smaller volumes of liquid extraction because they have smaller samples. And then the manufacturing side of the house, again, uses most of the time bulk product that's got to be separated. So that liquid extraction is going to look a little bit different. It's not going to be in nice little cutesy pieces of glassware, but it's going to be huge maybe, or big volumes of solutions and big kind of holding chambers. So again, that's how they're going to be different. Liquid extraction works because of the solubilities of the thing that you want. We all have a preference, ladies and gentlemen. I mean, if you even go back to elementary school and you were looking on the lunch menu, they gave you most of the time 2 choices. And they're like, you either get this or you either get that, right? Okay, so you got 2 choices here. So I either want tuna or I either want pizza. And it was like everybody did pizza on that day. I mean, I think only the teachers did tuna sandwiches. But now I probably would prefer that over that pizza. That's a piece of cardboard with, who knows, a mystery sauce and mystery meat on the top. Either way, that's a completely different conversation to have. But, okay, we get a choice. And we probably had a preference, and we gravitated to one over the other. Well, solutes, hello, work the same way, because solutes also have a preference. Oh, go figure. And that preference is something that we call miscibility or solubility. So these particles that we want to maybe keep or that we want to separate, or the molecules that we want to keep or that we want to separate, those molecules have a preference, and they are in something right now, okay? So, and the manufacturing process, they are part of the entire bulk that we have done in the very beginning stages of the processing. All right, so now that I've got this, okay, well, how can we get it out of there? Will evaporation work? Will condensation work? Will distillation work? Will filtration work? Will centrifugation work? I mean, what is going to go on? Well, this is another one of those options. So if I know that that molecule that we are after, that API that we want to gather and keep and capture, if I know that it has a preference, then I can give it that preference. And that could be in the form of a liquid. So what happens is that I would take a container, and that container has got my mixture of alphabet soup, whatever the case might be. It's there, it's ready. And then I will add into that container another solution. And that solution is going to go on top. But I've got to make sure that it is not miscible. All right, that's the key term. That means immiscible, and that means it will not mix. It cannot be miscible. It is immiscible, and they should not be mixing together. So whatever solution is there, I want to make sure that whatever I add to it will not mix and make one big solution. I want layers. That's the only way that this is going to work. So I'm going to add a new solution into that container, and then I'm going to jiggle. I'm going to act like I'm kind of making a cocktail drink at home. I promise I've not had one right now, but I'm going to act like I'm making or mixing something, and then I'm going to shake it up really well, and I'm going to let it sit, and I'm not going to disturb it. And we will see two layers. We will see a layer on top, and we will see a layer on the bottom. That molecule of interest that we are after, there is a chance that it was down in here, and this was all like the sludgy stuff. Maybe I don't want any of that down in there. I want to separate the good thing from the bad. So by incorporating a second solution, then that API is going to bloop, 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 go up here because it's the preference. I want the tuna sandwich. I don't want the pizza like everybody else. So we start to see a migration of that active pharmaceutical ingredient or that molecule of interest that we want, and it will go up into maybe the new layer that we have introduced. And now what can happen is that I can figure out how on earth can I separate that layer that is much cleaned up now, right? I mean, I'm getting rid of a lot of the trash. That's what this whole entire lecture has been about so far. I'm getting rid of a lot of the trash, and I've got a cleaner version and one step toward the final product isolation. Again, that's what this has always been about. So that other layer that's got all the sludgy, all the other things that we don't want, that can be waste. That can be disposed of. I don't need it any longer because hopefully I have done my liquid extraction properly. So that's what you're going to see here on the slide. It's just a way to remove impurities. Again, that's what this is all about. Maybe that second layer that you added, maybe the impurities go there, right? Or maybe that second layer that you've added, maybe the molecule of interest goes there. It really doesn't matter. I mean, we can handle it either way. And that's, again, the same story that we've talked about this entire time. Is it maybe the solid on the filter paper that you want? Or is it the filtrate liquid that goes through the filter paper that you want? In the centrifuge, is it the solid that you want? Or is it the liquid that you want? The same thing's happening here. In the liquid extractions, when you add the new stuff, right, and that new stuff does not mix and it forms a layer, okay, which one should you be keeping? Are the impurities going to the new layer and that's what you want to get rid of? Or is the active pharmaceutical ingredient going to the new layer and that's what you want to keep? So again, manufacturing can be totally different depending on what we're manufacturing, of course, and both of these are plausible scenarios that you would see. Another reason to do liquid-liquid extractions, you can reduce the volume amount, right? So if you play this kind of smart, that new stuff that you add, well, that new stuff, if it's going to go in and grab that molecule that you want to keep, well, you don't have to use a lot of it, right? I mean, compared to maybe that bulk product that you started with, maybe you can use a much smaller amount of that liquid, and if you do that, then you can somewhat concentrate that active ingredient that you want. So not only is this a purification step, but it's also in a way a condensation step, if you want to think about it that way, because you're making the concentrations stronger if you play it kind of smart. So you can concentrate the product, absolutely. It's not true condensation, of course, right? It's just the term that I used, but it is there. Very often it needs time. These things are going to be mixed because that's the only way that that new liquid can go in and grab the things that you want it to grab. And you got to give it time, right? It's like sending 50 kids into the playground and you're like, okay, tag, you're it. You need time in order for them to go out and tag somebody. Okay, it's not going to happen immediately. If so, what's the fun in the game? Well, the same thing's happening here. You got to wait. You got to be patient. You got to allow these liquids to separate into their layers, and that maybe eats away a little bit of time, which is one of the drawbacks possibly of the liquid-liquid extraction. However, the good thing with liquid-liquid extraction, now you're talking my language. You're cheap. I mean, that's great. All right, so compared to some of the other processes, liquid extraction really doesn't require a lot of stuff. It just needs a big old vat and it needs some solvent, and you just allow it to kind of naturally do what it needs to do, and your molecule of interest will leave one layer and go to the other one, and then it's just a matter of how do you separate that off. I mean, that's all that we've got to do. So there's no really utility needed in a way. There's no large amounts of heat that's needed to make this product go forward. There's not like a continuous big stir that needs to go on. I mean, yeah, you need to stir them in the beginning, but it doesn't need to continue. You need to stop it after a certain point. So very often, overall, these are way cheaper than some of the other operations that we've talked about. Here's an example of just a big old vat, and here it looks like it's water containing our product. All right, so that is kind of our alphabet soup, and we want that product to be removed. All right, so how do we do that? Well, we know that maybe water is the unpreferred dinner plate that molecule wants, or actually drink. So, okay, hey everybody, thanks for coming over. What can I get you to drink? And then that product is going to go, well, definitely not water. So I just need to give it an option, and I've got many choices of options that I can give it. So we get a solvent, and this one says, ooh, organic solvent, whatever that means, right? So we enter a solvent or another liquid choice or another drink choice into the pitcher, and that product is like, oh yeah, I see that, but how do I get up there? Well, you got to stir it, and that's what you're seeing here. All right, so we're going to stir, and we're going to agitate, and we're going to make sure that we mix all of these two things together, and then we stop it, and then we sit back and we wait. So by mixing these two layers, that product can actually be like, oh yeah, that's my drink choice, that's my drink preference, yeah, please. So it's going to slowly gravitate and travel with that drink preference, and that is going to be the new organic solvent that we have shown in the picture. So those are typically the three types of steps. Again, it looks a little bit differently in a laboratory setting. In a lab setting, what you would often see is something that is a piece of glassware, and it's really like we call it a separatory funnel, because that's exactly what it does. It separates, and we enter our water solution containing product into that separatory funnel, and then we add our new organic solvent into that separatory funnel, and that creates two layers because they don't mix. And then by hand, we actually pick this little separatory funnel up, and we rock and we shake and we mix those two layers, and then we put it back onto a stand and we allow it just to sit there, and we come back to it 5 or 10 minutes later, and those two layers have separated for us. And then what can happen is that we turn on the stopcock. That's what we call that at the very bottom. We turn the stopcock on, and then we can drain one layer, and we can stop it. That's why we call it the stopcock in a way. So we can stop it, and then we can switch our containers. So here is our old stuff that we don't want, and then I can put a new container up underneath, and I can open that valve back up, and then that liquid would drain into a new fresh container that will just really have our product that we want with not as many impurities that's coming along with it. So these are easily done by hand, but in the manufacturing side, as you can imagine, definitely not. We are using too big of a volume in order to pick up a little separatory funnel. Unless you're like the Incredible Hulk, it's not going to work for you. All right, so liquid extraction in industry, most of the time, when a solution contains impurities, you got to get rid of them, of course. So that liquid can pull your product that we've talked about already out of that solution, and it can isolate them. It might not be completely clean. So that's kind of the story here. You just got to keep in mind, it might not be 100% pure. That is an issue that we got to deal with later. But again, we're at least one step in the right direction, and that's really all that matters. Sometimes it will take multiple things in order to do the proper way, and it might be the end step. It might not be the end step. All right. Or it can separate the impurities. So again, it really depends on the solubilities. It really depends on the things that you're working with, and that's going to determine those types of judgments. Next up, liquid extraction can reduce the product solution volume because if it's going to go into that new layer, you've got control of that volume. You can make it as small as you want to make it. As long as you're ensuring that all of that product goes into that new liquid layer and you've got enough of that liquid to hold all of that product, then you will be perfectly fine. So you are making these samples more concentrated over a course of time. And next, at the very bottom of this slide, it says liquid extraction pulls product from the solvents that do not evaporate easily into the ones that do. So if I go back to this image, water has a boiling point, and water's boiling point is 100 degrees, right? So it's going to take a lot of time for that water to evaporate off. So if I drain that water layer off, and that's where my product is at, and only my product is remaining, then I'm going to drain it off, and maybe I just want to evaporate it. So slowly, over the course of maybe days or weeks, that water is going to eventually evaporate off, and I will be left with a residue or a liquid, and that would be the product that I'm after. All right, nobody has time for that. I don't have time for that, right? So instead, the other kind of nice option here is that when you add this new organic solvent, you can choose this organic solvent, and you can choose an organic solvent that has a really low boiling point. And boiling point, of course, is the temperature at which it begins to evaporate off. If you play off of volatility, which is the easiness of it to evaporate, and if you choose something that has a very low boiling point, so you don't have to heat it up in any form or fashion, then this organic solvent is going to evaporate quicker. And that's the great news with it. So let it evaporate as fast as it can. And maybe instead of days of waiting for the water to evaporate, I can come back the next day and all of that organic solvent is maybe evaporated already. If I play around with pressures and I turn a vacuum onto the system, then that pressure can actually lower the boiling point even more, and it can speed the evaporation up even faster. And then when that happens, maybe I'm not even waiting overnight. Maybe I'm just waiting a handful of minutes or an hour or so for all of that organic solvent to evaporate off. Common solvents that are typically seen in a laboratory setting and or manufacturing setting. The reason that these are common solvents is because, number one, good stuff, cheap. If you ever went to Ollie's and read their slogan, that's where that came from. I can't take responsibility for that one. But these are typically very pocketbook friendly. So they don't cost a lot of money. compared to some of the organic solvents. And number two, I'm not going to say they're somewhat universal, because they are not universal, but they do a very good job of really doing most, all right, most of the things that we would see on a daily basis. So these are going to be things like toluene, which you can purchase at Walmart. I mean, you as a consumer can purchase that chemical compound, that organic solvent. Phenol, that's also another one that you can actually purchase in a roundabout way in Walmart or some hardware store like Lowe's or Home Depot. Ethers. Ethers are exactly what you think that they are going to be. Ethers, number one, have very low boiling points, but just an ether molecule was an old anesthetic. I mean, that is what they would use to knock you out with before an operation happened. You woke up with an extremely horrible headache and probably an upset stomach after you would wake up from that. But ether was one of those first anesthetics that we used back in the day. So ethers can also be used. They make great solvents. They are fairly cheap. The problem here is that some ethers, though, they can be explosive. So if you're not very careful with some, not all, but with some of these, then they can blow up, and you want to use them fast. You don't want unlimited supply of ether at your location, because those types of things can actually cause you a disaster in the long run, especially if you're not actively using them very quickly. Ketones and alcohols are also going to be some of the common solvents. Again, you can purchase ketone type of molecules in Walmart, Home Depot, Lowe's, any of those big box stores, hardware departments, whatever the case might be. You will often see things like methyl ethyl ketone, so MEK and so forth. These are options for you. So, I mean, that kind of means they're somewhat safe. The answer is no, not really. You kind of want to still handle them with care. You don't want to go sniff the bottles. You don't want to go get high on them. And you can't actually. But it will give you a headache, and it can make you pass out if you're not very careful. So always use them in a ventilated space. But these notoriously are going to be pretty safe compared to some of the other organics that you could choose from. So pretty common health hazards, not the greatest health hazards compared to some of the other organics, so they're safer to work with, and again, very, very cheap. So that's why we see a lot of those as solvents. So here's just a connection point. When we talk about liquid injection, what you see up in the top right-hand side of the slide right now is actually a template for penicillin family compounds. You're going to see an R group, and this R group on that particular compound represents something random. The reason that is there is because we have different types of penicillin, and that is the little piece that begins to change depending on the flavor of penicillin that we get. And when I say flavor, I'm not talking about, oh, this tastes like bubble gum or this tastes like cherry. No, this is just an alternate form of a penicillin that has slightly been modified. And that R group is the piece that changes when everything else is pretty much the same. So notice there's no other R groups anywhere else. That means that template has to be there just like that in order for it to be classified as penicillin. So in the manufacturing of penicillin, what normally goes on is that we can take something like a moldy piece of cantaloupe or a moldy piece of bread, and we can isolate that biologic. And that biologic is going to be something that you would equate to as mold. And we can take that mold and we can grow a culture of it. And that fungus is really what that is going to be doing the product formation. So that fungus is actually what makes the penicillin that we can then prescribe to little kids that are sick, or to you that are sick, or whatever the case might be. Again, it can be in liquid form, it can be in a solid dose form, whatever the case that you need, we can make it that way. But all of this is getting done in a bioreactor. All of this is getting done in a fermenter. So we're allowing the mold or this fungus to kind of do its job. job. We're going to grow it. We're going to make sure it's a big, healthy colony. We're going to make sure that it's got enough water and food in order to keep growing and keep multiplying. And we just kind of need to be patient with that. So all of that's going to be kind of the upstream part of the process. So we're growing this nasty mold on your bread or your cantaloupes and stuff, and it's getting bigger and bigger and bigger, and the colony's getting bigger and bigger and bigger, and we're making it healthier and healthier and healthier. And at the same time, the next time you look at your moldy bread and you go, "Ooh, throw that away, I don't want it." Well, the next time that you take something like a penicillin, that's probably where that came from, or at least a variant of it. So at a certain point, you got to stop it. And when we stop it, what you'll see is that we're going to have to separate, and that's kind of what we've been focused on this whole time. We got to separate those cells off. So we got to get rid of the cells, and we need to isolate the pharmaceutical ingredient that we want. So those cells are in a medium, and use your words. I mean, we talked about that already. So the medium is the solution that this stuff is basically in. And that medium probably has the active ingredient that we want. So that liquid contains the penicillin, and now we need to get that liquid away from those cells. And one of the first things, of course, that we can do is filtration. Go figure. We talked about that. So we can filter the product, and all the liquid goes through the filter, and all of the sludge stays behind. And then once we get that liquid, we can look at the penicillin and we can say, "What would you like to eat tonight, penicillin? Do you have a flavor that you like? Do you have a preference that you want?" And of course it does. So this is going to be mainly water, and these are going to be nutrients, which are mainly going to be salts and those types of things. So we get this water layer, and we're going to add an organic layer. And that organic layer will not mix with water. They will separate into two. And when those two layers separate, that is great news, because what's happening is that if we give it a jiggle, 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 all of that penicillin will see that new drink of that organic solvent, and it will begin to migrate into that new drink, into that new layer, and we can pull out the penicillin using liquid extraction. So what you just seen is really a whole culmination of all of the separation techniques that we have talked about. Maybe not all of them, but quite a few of them. And I don't want you to forget about evaporation and distillation. All of these things can still be used, and we can still recycle those liquids. We can still recycle those organic solvents. So for instance, if that step required me to use something like toluene, that is okay. Again, pretty cheap, pretty safe to handle, as long as I'm not going in and sticking my nose into the vat. I mean, you know, that's great. But that toluene we can actually save. And that toluene is not going to give us a problem as long as we treat it the right way. What that means is that once I use it, and once it pulls out that ingredient that I'm after, then we can take that toluene and we can evaporate it to capture it. We can distill it to capture it. And if we do our job the proper way, that becomes clean toluene once more, or recycled toluene. And maybe we can go back into the earlier stages in the plant, and maybe we can reuse that toluene in some form or fashion, and we don't really have to dispose of it. We can just simply reuse that solvent until we get to a point that we can't reuse it anymore. So that's kind of a story of wrapping it up, not fully, because we've got another separation type of method that we want to talk about, but I think that it does, this one example did a very good job of gathering all of those individual little topics and putting it all together and putting it again in a nice little package with a bow, so I can give it to you and say separation. But don't separate from me right now. There's more videos along the way, so come back, take some more notes, listen up, make fun of me. That's okay. I'll never know if you do, unless I've got secret little bug microphones onto your computer. See you next one.